Okay, let's just dive right into probably the hardest question I've done on this channel in terms of the length of the question and the simplification that goes involved with it, and just like the put your head down and work type question, right? It's not like in terms of math it's doable, right? It just takes a lot of concentration and thinking and checking over your work. So let's just kind of dive right into it here. It's totally doable using the Laplace transform techniques that we already know. So let's say we have the third derivative of our function x minus 3 times the first derivative of our function x. That's going to be equal to Laplace, or not Laplace, sorry, equal to e to the power of t. And I'll say that for the initial conditions, x of 0 is 4, I'll go x prime of 0 equals x double prime of 0, and I'll say that's going to equal 7. Okay, so we have our function, the third derivative of that function minus 3 times the derivative of that function to the first degree equals e to the power of t. So x, remember, is our function. It's not like a variable that we can just plug in independently. And t is our independent variable for the function x of t. So I'm going to take the Laplace of both sides. So this is going to be the Laplace of d cubed x minus 3 times the Laplace of dx. It's going to give the Laplace transform of e to the power of t. Okay, now we have to kind of use our rules here. So we know for the third derivative, it's going to be s cubed L of x. So remember, x is just our function, minus s squared x of 0, minus s x prime of 0, minus x double prime 0, minus 3, and so 3 times the derivative of this whole thing. So remember, for the derivative, it's going to be s lx minus x naught, and that's going to equal, well, e to the t, the Laplace of that is just 1 over s minus 1, because remember, our lambda in this case would just be 1. So if we kind of simplify and plug in our values here, this will be s cubed. We still don't know L of x, right? And s is our new variable. So we're in the s domain now. And then minus s squared times x naught. So this will be minus 4x squared. Sorry, s squared. Okay, and then we're going to go minus 7s because x prime of 0 is 7. Going to go minus 7 again because x prime and x double prime are equal. Minus 3s times the Laplace transform of x, just kind of distributing that 3. And then we have minus 3 times negative x of 0. Well, x of 0 is just 4. Negative 3 times minus 4 is positive 12, so we got plus 12 here. That's going to be equal to 1 over s minus 1. Okay, cool. Now we can factor out this L of x and add the other stuff to the other side. So we get L of x times s cubed minus 3s. We're going to say that that equals 1 over s minus 1 plus 4s squared plus 7s minus 5. Okay. And now what we want to do is we want to divide by s cubed minus 3x by minus 3s on both sides, so we just get L of x. So for all these questions, we want to apply our differentiation rules. So instead of having derivatives, we just have things in terms of L of x and our initial conditions. And we always just want to solve for Laplace x, which is what we're doing here. It just can kind of get a bit hairy on the other side. So we're going to have the Laplace transform of x, which is what we want, equals, well, really what we're doing now is we are taking every term on the right and we're dividing it by s cubed minus 3s. So s cubed minus 3s, we can factor out an s. that could make a difference. So we're going to get 1 times s minus, I'll go actually s squared minus 3. And this s minus 1 was already there, so times s minus 1. And then we have, well, if we're dividing 4s squared by s cubed minus 3s, we're going to get plus 4s over s squared minus 3. Okay, plus, it's going to be 7 over s squared minus 3, because the s's will cancel, and 7s. And then we're going to have minus 5. Right, yeah, minus 5 over s times s squared minus 3. Okay, cool. So what we did was we just basically divided every term by s cubed minus 3s. So for the 5 here, the reason why there's only 2 terms is because nothing was on the bottom of the 5 other than the 1. So this term right here just kind of joined the bottom there. And for everything else, we could kind of cancel some stuff. And this is the longest one right here because there was already a denominator of s minus 1. All that good stuff. So basically when we simplify all this, we get these 4 fractions. So if we want to figure out what our function x is, right, and we've already applied the initial conditions, so we don't need to worry about that. But all that we need to do is take the inverse Laplace of everything. So I'll call this A, or actually, I'll call this W, X, Y, and Z, just because I don't have enough room to write it. So I'll go X equals the Laplace inverse of W plus the Laplace inverse of X plus Laplace inverse of Y plus Laplace inverse of Z. So we're taking the Laplace inverse of everything, adding it all up, and that should give us our function x. The only issue is we're going to have to use partial fraction decomposition for lots of these. Okay, so let's actually figure out if we can do any of these right off the bat. So this for sure not, because there's no rules in our table that have s squared minus 3, s minus 1. We can't really manipulate that in any way. S squared minus 3 with an s on the top. Well, let's think about that. Let's go to the top here. S squared minus 3. So that minus 3 is acting as our plus b squared. So if b squared, right, if b squared equals negative 3, let's see here. I'm just looking at what we can do. Yeah, so we can take the square root of both sides. We're going to get b equals negative square root 3 for both cases. So this will be negative square root, except the thing is, b squared equals negative 3. We can't just take that negative. So this will have to be, b is going to be equal to the square root of negative 3, which is I root 3. So it's going to be in the imaginary realm. So I root 3 is going to be 2 pi over the period. Let's just see here. So that's going to be for this one. So it'll be 4, if it was 4s on the top, yeah. 4s on the top there. It'll be 4 times the cosine of root 3 it. I'll go Laplace inverse. Equals, so it's going to be 4 times the cosine of root 3 it. Okay, Okay, now let's do, what other one do we have? 7 over s squared minus 3. So that's going to be this one right here because it's a constant. There's no s on the top. So 7 over, so it'll be 1 over root 3i sine root 3it. So inverse of, yeah, it was 7 over s squared minus 3. 1 over root 3i times the sine of root 3it. Okay, cool. And now, let's just see if we can do anything else. So we covered x and y, right? Now we need to do z and w. So let's figure out this kind of monster right here, how we can split this guy up. So I'll write for Laplace inverse of w, we have 1 over s times s minus 1 times s squared minus 3. Okay, so that's going to be equal to a over s plus b over s minus 1. And then we're going to have plus cs plus d over s squared minus 3. So basically what we did was we split this into 3 factors. 2 of them were linear. That's why there's constants on the top here, a and b. And then s squared minus 3, we need a cs plus d because this has to be a linear term if the bottom one is quadratic. And simplifying this, we're going to get 1 equals, a times s minus 1 s squared minus 3 plus b times s squared minus 3 plus cs plus d times s minus 1. Okay, so if we kind of have all of these lined up like this, we have to think about ways to kind of get rid of as many variables as possible. So first off, let's say let s equal 1. Okay, because if s equals 1, we plug 1 in for s, so this will be a times 1 minus 1, which is 0. So this thing will cancel. If it's 1 here, it'll cancel this whole thing. We'll get rid of the c and the d because we have an s minus 1 term here. So all that we'll be left with is, obviously, this side's 1 equals b times s, which is b times 1. So b times 1 minus 3. Well, 1 minus 3 is negative 2, right? So this would be 1 equals negative 2b. Therefore, b equals negative 1 over 2. So that's good. We've got that figured out. Now we're going to do the same thing. Think about what we can get rid of. Smartly choosing an s value. If we plug in 0 for s, we'll get rid of these 2 terms completely, so 3 variables there. So if s is 0, we're going to get 1 equals a times 0 minus 1, which is negative 1, so negative a times negative 3. So 1 equals 3a, therefore a equals 1 over 3. Okay, and now what we're left with is we're trying to figure out what c and d are. So what can we plug in for s that won't get rid of this part, but will get rid of these 2? Well, notice how these 2 share an s squared minus 3 factor where this one doesn't. So we can let s equal positive or negative square root of 3, because then if we plug that in, we're going to get 0 for this term, and that'll go away. So I'll say let s equal the square root of 3. Okay, so when s is the square root of 3, 1 second. Just gonna find my calculator wherever it is here. Not that I'll probably not use my calculator just because we'll be able to simplify it without it. but just for reference in case we kind of need to fall back on something. So if s was the square root of 3, right, and we kind of have this formulation up here, we know that these two terms are going to cancel, so all we have to worry about is the right side. So we're going to get cs plus d times s minus 1, so it'll be root 3 c plus d, right? So this would be our cs plus d. I'm just filling in s times root 3 times root 3 minus 1. This is going to equal 1. Okay, if we expand this out, let's do the root 3 into these two right here. We're going to get 3c plus root 3d. And remember, we still have this root 3 minus 1 equals 1. Then if we expand that further, we're going to get 3 root 3 c minus 3c plus 3d minus root 3d equals 1. Okay, now what we want to do is we want to solve for one of the variables, either c or d. Now that we expanded it, let's solve for things in terms of c. So if we factor out a c here, actually let's factor out a 3c because they both have a 3c. This will be root 3 minus 1, which is nice, plus, actually let's move that plus 3d to the other side, and the negative root 3d, so this will be 1 plus root 3d minus 3d, and if we solve for, let's just solve for 3c to keep things easy, not dividing by 3. This will be 1 plus root 3d minus 3d over root 3 plus 1, and root 3 minus 1, and root 3 minus 1 is a constant, but I just like to leave it in exact form, because when we round things, it's not as nice. So we know that 3c is equal to this expression in terms of d. Okay, now what we're going to do is we're going to let s equal negative square root of 3. And notice that if we say s is negative root 3, these terms still cancel because s squared is still positive 3. So this is positive 3 minus 3. That'll go away. And we do the same thing, plug in negative square root of 3 now into s. So we're going to get negative root 3 c plus d times negative root 3 times negative root 3 minus 1. That's going to equal 1. Now let's kind of expand this out. So we're going to get root 3 times root 3. They're both negative, so it's going to be positive 3c again. A lot of it's going to be the same because the negatives will cancel. But there's, I think, a couple, maybe 2 different signs in this variation here. And like I said from the beginning, this is like just a lot of concentration expanding out. So we're going to get negative 3 root 3c, right? That's going right there, multiplying, and then we're going to get plus 3d. Whoops. So that's another similarity. We had plus 3d before. That's because it's negative root 3d times negative 3. And then the other one, they're both positive. That's why it's still positive. Minus 3c plus root 3d equals 1. So now let's do the same thing we did before. Let's factor out a 3c, try and keep it consistent. And we're going to get negative root 3 minus 1. That's going to equal 1 minus root 3d minus 3d. And then let's solve for 3c like we did for the other one. So 3c is equal to 1 minus root 3d minus 3d over negative root 3 minus 1. Okay, so now that we've done that, I'll just kind of section this off. So this is 3c. Notice how this is also 3c. Since these both equal 3c, we can set them equal to each other. So even though we don't know what c or 3c is, we can solve for things in terms of d and then plug it back in to see what we get. Okay, so since they're both equal, we're going to say, okay, well, that must mean that 1 plus, 1 plus root 3d minus 3d over root 3 minus 1, so that was the original one, equals this new 3, so 1 minus root 3d minus 3d over negative root 3 minus 1. So notice the only difference between the two is that this sign here is negative and this sign here is negative. That's the only difference. So we had two positives, two negatives that kind of changed. Okay, so now that we have that, let's cross multiply. So we'll get 1 plus root 3d minus 3d times minus 3d, yeah. Oh, hold on. Oh, I see. Okay. One thing I did here was, hold on. So see how these are both negative like I was talking before? If we want to make those both positive so it's closer to this, because I like seeing the positive root 3 there, we can just make everything like the negative version of itself. So if we make both of these a plus sign now, we can get rid of, if these were both pluses now, so positive root 3 plus 1, we just change the signs here. So this will be negative, this will be plus, this will be plus. And we can do that because we're dividing the top and bottom by negative 1. And if we do that, it doesn't change the value of anything. So now we're going to get 1 plus root 3d minus 3d times root 3 plus 1. Oh man, this pen. Plus 1 equals negative 1 plus root 3d plus 3d times root 3 minus 1. Okay, so now that we set this up, we have a few things that can cancel after we expand. So quickly, let's just expand it out. We're going to get, we're going to get root 3, right, 1 times root 3 plus 3d minus 3 root 3d plus 1 plus root 3d minus 3d, and then I'm going to go negative root 3 plus 3d plus 3 root 3d plus 1 minus root 3d minus 3d. Okay, so now that that's all expanded out, let's see what we see on the left and right side. I see, what do I see? Do I see a 3D? Yeah, I see a 3D on both sides I can cancel. I see a 1 on both sides I can cancel. And I see a negative 3D I can cancel on both sides. So let's just rewrite this so it's a bit cleaner. We're going to get root 3 minus 3 root 3d plus root 3d. We can see we're going to be able to kind of bring some terms together, equals negative root 3 plus 3 root 3d minus root 3d. Okay, so root 3, no like terms there, but we have negative 3 root 3 plus root 3, and those are both in terms of d, so it'll be root 3 minus 2 root 3d. And then on the other side, we're going to have negative root 3. We're going to have plus root 3d minus root 3d, so it'll be plus 2 root 3d. So what we're going to have now is, well, let's get all the d's on one side, so we add them there, and then we move over the negative root 3, so we're going to get 2 root 3 equals 4 root 3d. This is actually going to turn out pretty nice. divide both sides by 4 root 3, we're going to have 1 over 2, because 2 root 3 over 4 root 3 simplifies to 1 over 2. That's going to be equal to d. Okay, and when we plug in d equals 1/2 into this original equation, we're going to see that this side equals 1/2. So if we put in 1/2 everywhere we see d for either of the equations, we're going to get 3c equals 1/2. So therefore, c equals 1 over 6. Okay, so when we kind of rethink what all these numbers meant, remember we wanted it to be cs plus d. Now that we know our c is 1/6, 1/6 s plus d, which is 1/2, and remember that was over, well, for our cs plus d, that was over s squared minus 3. So s squared minus 3. If we multiply the top and bottom by 6, notice how this will be just s plus 3 over 6s squared minus 3. Okay, so now that we know this is our cs plus d term, actually what we could do is split it up even more. So if we multiply it by 6, this will be s over s squared minus 3, and then split it up again. So we get plus 3 over s squared minus 3. And I don't like writing it like this because we can combine these fractions, but taking the Laplace of both of these will be a lot easier. So we're going to get our original Laplace transform 1 over s times s minus, well, actually, I'm not going to write the whole thing out, because remember when we solved before for the inverse Laplace of w? Where did we go here? Yeah, so the inverse Laplace of, x and y, we already solved those. So we wanted the inverse Laplace of this part right here. So that was equal to, well, for our original fraction, 1 over s times s minus 1, s squared minus 3. We now know that that can be equated to 1 over 3s, because remember our a was 1 over 3 that we found way back up here. B was 1 over 2, so this would be minus 1 over 2 times s minus 1. Just plug in our values, and we're going to get plus s over s squared minus 3 plus 3 over s squared minus 3. Taking the inverse Laplace of all of those, let's see here, so 1 over 3s, going all the way back up here, 1 over 3s. This is just 1/3 times 1 over s. So this will be a third of, well, if we just think of 1 over s, this will be 1 over s to the 1. So this will be t to the 0, which is 1 over 1 minus 1 factorial, which is 1. Oh, right, and that makes sense, because if we have 1 over s, we just get 1 back. So we actually could have used this one right here. So it'll be 1/3 of 1, which is literally just a third. Yeah, so this will just be a third. So I'll call this part, this was our w, so the inverse Laplace of w equals, equals 1/3, okay, minus 1 over 2, and then if we have s minus 1, if we take the inverse Laplace of that, s minus 1, that's going to be e to the t, because lambda is 1, so minus 1/2 e to the t, 1/2 e to the t, s over s squared minus 3. Well, remember we already did that. If we have an s over s squared minus 3, where did we do that? S over s squared minus 3, yeah. So it was this one right here, except we don't have a 4 this time. So it'll just be cosine root 3 it plus cosine root 3it. And then if we have 3 over s squared minus 3, this would just be plus, how did we do it before? This was 7 over s squared minus 3. Now we have 3. Oh, so this will now be, I should have written it here, 7. So this will be 3 over root 3I sine root 3, okay, 3 over root 3I. 3 over root 3I sine root 3it. Okay, so we just solved for the inverse Laplace of w. Okay, that's good. I'll kind of branch this off. Now just the last step is, what didn't we do yet? We just got to do z. So we have to split up 5 and s, and then s squared minus 3. 5 over s times s squared minus 3. So 5, whoops, my bad here. Why won't it let me go in? Okay, that really sucks. Why won't it let me go in here? There we go, finally, thank God. Sorry about that. So 5 over, what was it? S times s squared minus 3. Okay, so this is what we're trying to split up. We're going to get a over s plus bs plus c over s squared minus 3. This is a bit simpler now because we only have 2 terms. So let's go ahead and multiply both sides. So we're going to get 5 equals, well, this will be a times s squared minus 3 plus s times, so bs plus c times s. So let's see here. If s is equal to 0, then this whole term will go away, and we'll just get 5 equals negative 3a. So a is going to be negative 5 over 3. Okay, now if we want to solve for b and c, right, we're going to say, well, let's say s is positive root 3. So I'll say let s equal positive root 3. In that case, we're going to get 5 equals root 3 b plus c times s. So that'll be, s is root 3, so it'll be 3b plus root 3c. 3b plus root 3c. And then if we say let s equal negative root 3, we'll get the a gone as well again. So it'll equal 5, and I'll just write an equal sign here, equals negative, so that'll be 3b again, minus root 3c. Okay. So if we know that that equals 5, let's solve for c. Actually, no, let's solve for root 3c. So if this part here is equal to 5, then 5 minus 3b equals root 3c. And here, this will be 3b minus 5. Root 3c will be equal to 3b minus 5. So 5 minus 3b in that case will be equal to 3b minus 5. So if we add it to both sides, we're going to get 10 equals 6b. And in that case, b will be 5 over 3. And that is kind of cool because a was negative 5 over 3. And if b is 5 over 3, we can just plug that in. So 5 over 3, so 5 minus 3b was equal to, what was it, root 3c. So minus 3 times 5 over 3 equals root 3c. Well, the 3's will cancel here. We get 5 minus 5, which is 0, equals root 3c. So c equals 0, which is always nice. So in our bs plus c here, we're going to get negative 5 over 3s. So negative 5 over 3s. I'll write z here, z negative 5 over 3s. And then for the bs plus c, that'll be, so our c was 0, so it's just going to be bs, which is over s squared plus 3, so plus 5 over 3. And this was 5s, s squared minus 3. Okay, taking the inverse Laplace transform of that, we get 1 over s. This will be just negative 5 over 3 for this part here, because 1 over s is just 1. And then, holy smokes, this is pretty crazy. Plus 5 over 3. So it'll be s squared minus 3. We see that again. So it'll be, when we had the s, what was it? I'm just going to keep checking the chart. So s over s squared cosine bt. Okay, so this will be 5 over 3, and then root 3i. Hold on. Let me just go back. Cosine bt. Yeah, so this will be 5 over 3 cosine root 3it. Cosine root 3it. So this is the inverse Laplace of z, inverse Laplace of w, inverse Laplace, this was x and y, so 4 cos root 3it. So I'm going to write our final solution here. We solved for all of them. It's just hard to kind of go back and forth. I'm actually going to copy and paste them. Actually, okay, so for our solution, copy this guy, bring it down here. So that'll go right there. So I'll just copy the other ones we did. If I can ever find them, I'll square them off and then we can. Okay, so this is our x, and this is our y, which I kind of indicated there. And I'm going to copy all this. Okay, copy there. So for our solution, remember we said the solution of this will just be all of these added up. So I'll write, remember x was equal to inverse Laplace of w plus x plus y plus z. So if we just add all those up, it'll be negative 5 over 3 plus 5 over 3 cosine root 3it. I'll actually just copy this itself as well. Actually, I'll do it in order. So w was right here. Copy. So I'm going to paste that, make it a bit smaller. Okay. And then we're going to have w plus x, which was right here. So I'm going to go 4 cosine root 3it. And of course, we have a plus sign in there. So we'll go plus. And then x, and then y. Remember, y was right here. Whoops, y was right here. So for y, we're going to get paste. I'll do it here, actually. Make it a bit smaller. Plus. And then lastly, we had our z, which was right here. And then we're just going to see if we can combine like terms, which will be fun. Then we're going to get minus that. So that is our solution right there for x. Now, if we can combine like terms, let's see. E to the it, that's going to stay the same. Cosine root 3it, cosine root 3it. So this will combine to 8 over 3 cosine root 3it. So that's gone. Because this is 3 over 3, and then this is 5 over 3. We're just adding those. And then, we also have 4 cosine root 3it. So that's 12 over 3. So that'll be 20 over 3. Okay. Cool. Now the sine ones will also combine. So this will be 10, right? Because we have 3 over root 3i and then 7 over root 3i. So that'll be 10. So plus 10 over root 3i sine root 3it plus, okay, so that's gone now, negative 5 over 3 plus 1 over 3, that's negative 4 over 3. So I'll go minus 4 over 3. So that's gone now, and all we have left is just minus 1/2 e to the power of t. And then that's gone, and it looks like we've kind of simplified everything. So this is actually our simplified solution with all the like terms combined. Okay, and that's your answer there. So if you were to plug in your initial conditions there, the requirements should be met. I'm praying. It's just tough because now we're in the imaginary realm. But that's okay because we're using sine and cosines for it. So we should be able to kind of use, the Euler characteristic and that kind of thing to figure out an equivalent real value for the value of this. And when we plug it in for the derivatives and all that, it should also work. So using Laplace and partial fraction decomposition, we effectively solved the solution. It's 4 terms that are pretty ugly, but I think we did a pretty good job. So thanks for listening. And yeah, this kind of concludes my mini series for Laplace transforms. I did, this is kind of an introduction. As hard as this is, it can definitely get harder. But Laplace transforms, my goal was to introduce to you the table of Laplace transforms, how to use them, what the Laplace transform was, right, where it came from. Remember that original integral we did? That's what the Laplace transform is. It's an integral with the same transformation properties, right? It's linear. We can factor things out, all that good stuff. So yeah, I'm not going to go any further with this series for the Laplace transforms. I think you guys have a good basis of what it really is. We've gone through lots of examples, and I've shown you the implications on differential equations, how we can solve it. And yeah, thanks for listening. I'll see you soon.